l'homme in l'Orient. And so it puts into collaboration two different universities, the University of Waterloo in Canada and the University of Science of Tokyo. So to describe this investigation, I decided to explain to you the biomimicry toolpath that we use to go from our material, which is an hygromorph biocomposite, towards, okay, how could we remove the lock that we know today with this kind of material, towards the final prototype, which is directly inspired from nature. So let's first talk quickly about what is an hygromorph biocomposite. I will be quick on this point because Antoine explained it to you before. So an hygromorph biocomposite is a new range of shape-changing materials, which is based on the motion of the pinecone scale. So if we look closer to a pinecone scale, we can see that this is made of two different layers, which will not expand the same way when the water will go through the tissue. So there is one layer which will swell highly, which will have a high hygroscopic expansion, and the other one which will swell not so much and will have a low hygroscopic expansion. And this difference creates a swelling differential, which generates the motion of the scale. So based on this principle, scientists design hygromorph biocomposites, for example, by using continuous flax fiber, which is the one that we use, and different biopolymer to create, so in a way that depends on the way you distribute the fiber, that you can generate a differential swelling, which create motion. So here you can see that this is the orientation of the fibers, which generates the swelling and the curvature. So if we want to look now more on a mathematical way, this is directly related to the Timoshenko's equation, which connects the curvature of the bilayer to several architectural features. So there is the thickness ratio between the restrictive and active layer, the stiffness ratio, and the hygroexpansion coefficient, which is directly related to the material. So this was briefly to remind you what is an hygromorph biocomposite. So now the log that we know with this material is the following. So we know that in our material, so this is a section of the filament that we print, we cannot exceed a specific fiber volume fraction, and this is problematic for us because we know that the fiber is the actuator inside an hygromorph biocomposite. So this is a fiber which swell and which generate the motion. So if we can't exceed this flax fiber content, in our case this is flax fiber, we are going to have a limited potential for the hygromorph biocomposite. Besides, we use several biopolymer matrix, which are quite hydrophobic, meaning that they are not very sensitive to water, and so that will prevent also the development of these smart materials. The conclusion of that is that we are able to do some structure which can exhibit specific shape changing as curvature, for example, or also twist if we change the distribution of the fiber. But this remains very simple response. So we would like to complexify this response. And in another way, and maybe this is the most important part of this investigation, we would like to make the response quicker. We would like to increase the kinetic of response of the material because this is quite long, as you can see in this picture. So this is definitely something that we want to do to exacerbate the potential of hygromorph biocomposites. So now, because I'm in a lack of time, I will directly focus on the natural concept, which is quite related to the bio-inspiration. So what I told you just before is that we, of course, take the pinecone scale as an example to design hygromorph biocomposites. So to sum up, moisture uptake and the bilayer configuration inside the pinecone scale generate actuation. But what has been recently observed in the scientific community is that there is a third layer which has to be considered. So in the pinecone scale, there is the sclerenchyma layer, which represents the restrictive layer. And inside the sclerid layer, which is the active layer, the one which generates the expansion, there is a porous part and a rigid part. And so from this investigation from Quan, we decided to look further to the role of porosity inside pinecone scale, but also inside natural systems, because we used to see porosities as a flaw in the material and design conception. But how could we use this porosity in a way to develop and to exacerbate the actuation of smart material? So if we look at natural examples, so the pinecone scale is made of a porous layer, which allows to restrain the internal stresses during the morphing. And so that helps the scale to get a better reversibility of the bending process. But there is a lot of other examples, for example, as the softwood, which has porous canals such as tracheids and pits, which control the flow resistance and the kinetics of diffusion of water through the tissue of wood. Same observation can be made also in hardwood, where there is a distribution of the porosity of the canals, which promote the supplies of water through the tissue. If we look at the fiber that we use, the flax fiber, this is made of lumen, which is a porous canals that can also be ascended by water by capillary mechanisms. And finally, in porous flax stem, the canals can be useful for providing nutrients to the different parts of the stem. So this is just to give you an example of which kind of porous structures we can find in nature. And there is so much more. So now that we know that, we wanted to know, okay, how would the porosity that we could design inside biocomposite help us to exacerbate the properties of hygromorph biocomposite? So, and the first question that we need to answer is, how does the porosity impact the swelling of the material and so the hygroscopic properties? So just to be clear here, I spoke a lot at the beginning about our material, which is a continuous flax fiber with a specific biopolymer. But to start this investigation, we wanted to use it on wood fiber filament with, sorry, I forgot to mention, with discontinuous wood fibers filament. Because we had, for now, technical problem to design this kind of porous structure with continuous fibers. So this is why we wanted to carry out this investigation, firstly with discontinuous fibers for process purposes. And by creating the canals, which is directly related to the printing path, we want to understand how does the porosity content inside the material affect the hygroscopic properties, but also how does the porosity distribution, so for the same porosity content, how does the diameter of the canals modify the hygroscopic properties, and finally, the cell wall thickness, so for the same diameter, how does the cell wall thickness impact these properties? So during this presentation, I will just focus on this part of the investigation, the impact of the porosity content. And so the first point that we needed to understand is how does it affect the water sorption? So here I took the same scheme, but you have to imagine the same material totally immersed into water. And so the water can go through the tissue directly, but also through the canal. And so what we add here as a result is that here you can see the evolution of the moisture content as a function of the immersion time. And so for very porous structure with 12% of porosity, we are going to get a very higher and also quicker sorption compared to unporous structure, for example, as the black curve show, with 0.6% of porosity. So this point needs to be taken carefully, because of course we have a higher water sorption at saturation, but that might be due to the fact that there is still water inside the canals. So this huge difference between the weighting samples can be explained by the free water molecules inside the canals. But the point which is very interesting for us is about the difference of kinetic of sorption, because we can see that for very porous structure, we are going to get a 3 times higher kinetic of sorption than for unporous structure. And that might explain that the water can go through the tissue more quickly. And so that can help to get a faster kinetic of response looking at the hygromorph biocomposites. So this is something that we definitely want to know. Now, knowing how does the water absorption goes, we need to understand the hygro expansion process. So as I explained to you, the water will go through the tissue and the expansion of the material will appear in the three directions. So in the Z direction, transverse direction, Y, and also in the direction of the fiber, so epsilon X. So there is a lot of value. You have the amplitude of the expansion regarding the direction that you consider, and also the kinetics of expansion looking at this three direction. And the point that we want to highlight here is the difference that you have here on this specific parameter between the kinetic of hygro expansion in the transverse direction. Because the transverse expansion is the expansion which governs the motion inside hygromorph biocomposites. And here you can see that we can increase this parameter by using porosity because the water can go faster through the material, and so the hygro expansion mechanisms starts quicker. So now that we understand how it affects simple biocomposite, we need to look at the final prototype that we want to design. Because this was just for simple biocomposite without any variation of fiber distribution. But what we have in mind right now is to use our continuous flux fiber and to design canals thanks to the commercialized Leu filament, so the discontinuous wood fibers filament, to create our smart actuators. So here you can see the canals, which has been designed with a porosity content of 5%. And we tested different porosity content. So here you don't have any porosity, and here you have 10% porosity. So first look was given to the responsiveness of the material. Is there a difference of curvature at saturation? So here you have picture at dry state and at wet state for each of these samples. And what we can first say is that there is not so much variation looking at the final curvature, meaning that the porosity content might not be so influent on the responsiveness of the hygromorph biocomposites. Even if this result needs to be taken very carefully, we need to do more tests to confirm this trend. But this is what we observed in a first try. But what is very interesting is looking at the reactivity of the material. Here you can see the curvature of the material as a function of the immersion time. And you see that the response is so much quicker when we use porous structure than when we use unporous structure, meaning that the response will happen faster, even if at the end we got the same amplitude of curvature. And that's something very interesting if we want, for example, to complexify the response by imagining hygromorph biocomposite with sequential responses. So this is why using porosity might widen the actuation potential of hygromorph biocomposites. And that's would be a great conclusion for us if we can confirm once more this trend. So now, if I have to sum up the conclusion, I would say that the porosity distribution helps to trigger the actuation of hygromorph biocomposite and, in a way, also the porosity content. Their activity is promoted by the capillary due to a faster absorption and diffusion of water, because water can go through the tissue quickly, and so that will make the hygro expansion mechanisms faster to start. The responsiveness is not, for now, an impacted parameter, but we need to once more be careful about this conclusion. And the perspective that we could imagine is to create this kind of material with sequential response to complexify the final shape of the moisture-induced shape-changing materials. So I would like to thank you for your attention, and do not hesitate if you have any question. I'm here to answer.